Hi everyone, this is Chenchuan Xu. I'm currently working on my graduate degree at Dalian University of Technology, and I am going to introduce our work, Relational Learning with Hierarchical Attention Encoder and the Recoding Validator for Few-Shot Knowledge Graph Completion. And I will introduce our work in the following 4 parts. At first, let's come to the introduction section. As we all know, that most knowledge graphs, such as Yago 3, Freebase, Neo, are still suffering from the problem of incompleteness, where quite a large number of relations in existing KGs have the long tail and the low resource problem. But most of previous KGC models, based on ChainCE, ConverE, and so on, require sufficient training triples for every relation to learn expressive representations. So, it is necessary to study the case where only a few training triples are available, and this is called Few-Shot Knowledge Graph Completion, as known as FKGC. Here is a definition of FKGC. Given a support set which have a few triples corresponding to a few-shot relation R, the FKGC task predicts the possible tail entities for a query set, and the task is called K-shot KG completion. Next, we come to model design. We proposed a novel FKGC models named HARV, of which consists 4 main parts. 1. A multi-layer neighbors aggregator with hierarchical attention, and a few-shot relation encoder, and a relation recoding validator. Finally, a matching network for support and query set. We first structure the neighbors of each trip in the support set S and the query set Q into multi-levels, and obtain the representations of head and tail entities by aggregating the neighboring information through the hierarchical attention mechanism. Next, we encode the representations of support entity pairs and their neighbor relations, respectively, to obtain the original representations and the recoding representations of the few-shot relations. Then we will calculate their loss function. Finally, we compute the matching score of the query and the few-shot relations representation. As the first part, we introduce a unique hierarchical neighbor aggregator to represent central entities. Specifically, based on the understanding of the triple structure, we define separate layers between the head entity and the relation called relational layer, and between the entity and the relation, we defined entity level layer. In the relation level layer, we utilize a set of neighbor relations to represent the head entity H, and through the entity level attention mechanism, we obtain the attention weight of the second level. Then, we multiply 2 attention weights to obtain the trip level weight. And we aggregate neighbors through applying trip level weight to obtain the final representation H of the central entity, which is EH. With the above steps, we can encode triples head and the tail entities in the support set, respectively, to get their representation H and T. Then concat them to get the embedding S of entity pair. We also introduce a bi-STM few-shot relation encoder to aggregate support set and get the first representation of few-shot relations. But encoding few-shot relations with only a few short of entity pairs may easily cause overfitting, while the dependence of the representations of relations on entities will gradually increase with the training process of the model. In order to reduce overdependence between relations and entities, and to further verify the effectiveness of BiSTM for coding relations, we introduce a second way to obtain their representation, using the neighbor relations of the support set to encode the current relations. Finally, loss validation will be added to the foreign ranking loss function, which is used to verify the correctness of the few short relations and their representations. Next, we'll introduce matching score and loss function. The role of the matching network in our model is to measure the similarity between the query set and the few short relation representations. Last, we will combine the validate loss function to obtain the final loss function of the whole model. That's all. And next, we come to experiments. To evaluate our method's effectiveness, we compare it with two groups of baselines, including 4 KG embedding methods and 2 few-shot relational learning methods in 2 datasets, NEO and Wiki. The result shows that our methods performs better for solving few-shot issues compared with traditional KG embedding methods. And second, compared to the 2 few-shot relational learning methods, our method performs better than both G-matching and and FSRL in the most metrics. Next experiment is ablation study. In Model 1A, we reduce the number of attention layers and keep only entity-level attention values to represent the central entity. In Model 1B, we replace hierarchical attention aggregator with 2 mean pooling layers over all neighbor embeddings. In Module 2A, we replace the recurrent autoencoder aggregation with a mean pooling operation. In Module 2B, we replace the attention weight of the aggregator with the mean pooling layer. In Module 2C, we replace BiSTM with just LSTM in encoder networks. And finally, in Module 3, we remove the whole module, which is relation recoding validator, from HARV. And the final result shows our model largely outperforms the variance, and it demonstrates the effectiveness of 3 main parts mentioned before in our model. And next, come to case study for hierarchical attention. HARV structures the one-hop local graph into relation and entity layers that aggregate neighbors through a hierarchical attention mechanism. By studying cases of hierarchical attention, we can analyze how heterogeneous neighbor relations and entities influence in representing central entities. And the result shows that our model is able to aggregate fine-grained information in local graphs effectively. We can analyze results on different relations from 2 aspects. First, comparing the result of each model longitudinally, we find a great variability in the results for different tasks. We speculate that the number of candidates sets for different task relations is an important reason for the model performance. And second, comparing the results of the different models horizontally, we found that overall our model performs the best, obtaining the highest results in 7 out of 11 tasks and having a relatively good level of predicting results for the rest. Finally, we come to conclusion. And at first, we introduce a hierarchical attention mechanism, which can aggregate heterogeneous neighbor relations and entities. Furthermore, we propose a relation recoding validation mechanism that strengthens the importance of relations, reducing the dependence on entity embedding and increasing the robustness of the model. We propose a few-shot relational learning model, HARV, to address few-shot knowledge graph completion tasks. And finally, we conducted comparison experiments on both the naive and the wiki datasets. And the results show that our model performs better than the state-of-the-art baselines. Okay, my presentation is over. Thank you.